A thunderstorm builds, and a massive discharge of energy tears through the sky. We have all seen lightning, or at least felt the crackle of a static shock when taking off a sweater in dry weather. The first recorded observation of this effect dates back to ancient Greece, around 600 BC. Thales of Miletus noticed that rubbing fossilized tree resin, known as amber, allowed it to pull light objects toward it. The Greek word for amber is electron. Centuries of careful experiments revealed a strict rule governing these interactions. Matter carries a physical property called electric charge, and it comes in exactly two types, positive and negative. Opposite charges pull toward each other, while identical charges push away. Whether it's a spark on your fingertip or a massive atmospheric strike, these events are the macroscopic balancing acts of these invisible fundamental actors. We know charge is a physical property because we can measure it. Early scientists developed devices like the gold leaf electroscope. When a charged object touches the top, charge flows down, and the two metal leaves repel each other. Invisible charge translates directly into physical movement. Charge doesn't exist on a smooth, infinite sliding scale. If you zoom in close enough, you find that all free charges are whole number multiples of a basic unit. You cannot have half a charge. It is quantized, counted out in discrete, individual packages, much like physical coins. Like a currency, these units cannot be conjured out of thin air or destroyed. When you rub a glass rod with silk, you are simply transferring electrons from one material to the other. The total amount of charge in the isolated system remains exactly the same. How these charges behave depends entirely on the material they sit on. Conductors, like metals or the human body, let electrons flow freely. Insulators, like glass or dry air, lock them firmly in place, forcing the static charge to build up. This brings us to a major physical problem. If charges are securely trapped on two separate insulators, with nothing but an empty vacuum between them, how do they push or pull on each other? How does force cross completely empty space without touching? In the late 18th century, Charles Augustin de Coulomb set out to mathematically define this mysterious action at a distance. He designed a highly sensitive instrument called a torsion balance to measure the incredibly faint forces between tiny, charged spheres. His experiments yielded a precise formula. First, force between two charges is proportional to their size. Increase the magnitude, and force scales up. Second, it is inversely proportional to the square of the distance. Pull them apart, and the pull weakens exponentially. Coulomb provided a perfect mathematical formula to predict electrostatic force, but he left the physical mechanism, how the force actually travels, completely unexplained. For complex systems with multiple charges, physicists use the superposition principle. You simply calculate the forces between every individual pair of charges and add them together. One charge's interaction is unaffected by the presence of others. Looking closely at Coulomb's equations reveals a glaring physical paradox. The math implies that if you move one charge, the other charge across the vacuum feels the change in force instantly. We now know the universe has a hard speed limit. Nothing, not matter, not information, nor physical force, can travel faster than the speed of light. Because instant action at a distance violates this universal speed limit, our understanding of how charges interact requires a radical update. Michael Faraday solved the paradox by changing how we view empty space. Faraday proposed the electric field. A charge creates a physical distortion in the space immediately surrounding it, rather than reaching across a void. When a second charge enters this area, it interacts directly with the local field distortion at its own coordinates. This solves the paradox. If the source charge moves, the change ripples outward through the field at light speed. The force is no longer instantaneous. This discovery established empty space as an active, physical arena that dictates how matter interacts. To map this environment, physicists use field lines. These trace the exact direction a positive test charge is pushed when placed in the field. These lines form continuous curves, flowing from positive to negative, and they never cross each other. You can read the strength of the field by its density. Where the lines crowd together, the electric field is strongest. The static shock you feel is the sudden, visible collapse of an invisible web of electric fields, the hidden geometry permeating the entire universe.